Thank you very much, Dave. Good evening, everybody. Um, in my time in Glenrock Middle and High School, I had a rather unique situation. Middle school on one side of the building, high school on the other side of the building. So some years a middle school schedule, some years a high school schedule, some years personality. But I taught everything from seventh grade math through non-AP calculus. And one of the things that I had to do when I was teaching this non-AP calculus course was think of some ways to introduce limits to students that were not using the delta epsilon definition that we traditionally see in calculus books. In the chat, there is a link to a document there. That is the handout for this evening, the problems we will be discussing. And in addition to having the problems, you also have screenshots for a variety of platforms. But at any rate, I thought came across some problems like these in an Algebra 2 book, Discovering Advanced Algebra, and I thought it would be a good, non-threatening way to get students familiar with what a limit is. And they're all around us. People don't realize it, but we deal with them on a regular basis. So I'm sure for those of you who've been able to see my screen, let me back out here a minute and go to the main menu and clear things up. Usually, if you have some kind of oral surgery, tooth pulled, root canal, you may need to take some kind of antibiotic over a period of time. Sometimes you get a superdose. So in a situation we have here, we have somebody taking a superdose of 800 milligrams of Trimox, which is also known as amoxicillin, on the morning of the procedure, and then 200 milligrams every day for 2 weeks. But one of the things that happens in the 24-hour period during the day is that the body processes it. So you lose 50% of what's in the body that you've taken from a previous time. So if we were going to model this, notice I have some questions here that are related to that you could use in a handout for students. But when we think of the seed number for a sequence, we think of the initial value. So we're going to type in the seed number on the home screen and store it. And let's think of what goes on during the day. The body processes 50%. So that is the decay rate. And one of the things we have to use in a sequence is we have to think of the decay factor. So if we're processing 50%, that means 50% remains in the body. So let's multiply 800 by 0.5 or 50%. So that means the following morning, person has 400 milligrams in their body. Now they take their daily dose for the first time. So let's add 200. And now they got 600 milligrams in their body. Now, the process is going to continue on a daily basis. And we can too put these two steps together. What I can do is take our last answer, multiply it by 0.5, and then add 200. So what has happened is we took half of the 600 and got 300, and then take another dose. So now it's 500 milligrams on day 2. But as you can see on the home screen, this process can be cumbersome. You could do it in Algebra 1 class. Let's go to the sequence menu. And as you can see here on the sequence menu, we think of a sub n plus 1 as the next term and a sub n as the current term. So what we are going to do is we are going to multiply the previous term, which is the current day, by 0.5 times a sub n. Let me go back and put a multiplication sign in, like we did before, and then add the 200. And then press execute to store. Now, the next step we have to take is we've got to set up our table. And if you notice, Part C asks about the level of medication in the patient's body after 1 day, 5 days, 2 weeks. That's the questions we want to ask the students. So let's go to table set. And we're going to set this up to go out for 30 days. Well, we're going to start at 0. Let me delete that. We're going to start at 0. And just for fun, we're going to go out to 30 days. And since we're using a sub 0, which is the initial value, the 0 day, the starting day, we're going to make that 800. Press execute to store. Press exit to return to the home screen for the recursion menu. And let's look at our table. So as you can see here, day 0, 800 milligrams. Day 1, 600 milligrams. Day 2, 500. So we can scroll through the table to see what's going to be happening over a period of time. So as you can see, the numbers are dropping. And if I was in class, time permitting, I might ask the students to take a guess as to what do you think the limit might be? What do you think the threshold amount of Trimox will be in the body? And it looks to me like if we keep going, we're approaching a limit. It's going to be 400. Now, let's take a look at the graph. Pretty picture. We can see how we have a limit here. So we are approaching 400 milligrams with that initial dose. Now, I'm going to skip ahead here and go to part E, because let's say the person, instead of taking 800 milligrams as a megadose, takes 1,000 milligrams. So if I go back and go to my set and change that initial value to 1,000, exit, store it. I'm not going to scroll through the table. I'm going to go to the graph. We got a limit of 400 again. Pretty interesting. So no matter, it seems if the seed number is greater than 400, the limit's going to be 400. What happens if we make that initial seed number 200? Press execute to store, exit to go back. We can scroll through the table if we want, but the graph's a prettier picture. So now we were approaching that limit of 400 from below as opposed to above. So no matter what dose the person takes on their first day, if they take a regular dose of 200 milligrams and the body processes 50% per day, they're going to end up with a threshold of 400 milligrams in their body. One of the things we have to keep in mind here in a situation like this is that the quantity of the drug in the body from one point in time to another is always going to be proportional. Now, let's go back to part C. Let's say the person stops taking the drug. So that means the body's just going to process 50% per day. How many days will it take for them to get less than 1 milligram in their body? So what we can do is we can put in a restriction. Parentheses, I'm going to go to catalog. And I'm going to store the less than or equal to sign. Let me put my variable of n in here. And we want to go with 14, less than or equal to 14. Let's press execute. Let's go back to our table that we had. Well, let's see here. I got to go press exit and change my set with the initial value of 800. And let's go and look at the graph. And let me trace through the graph. So notice we get out here to the 15th day. We're at 400 milligrams. Now the 16th day, it drops precipitously. So we have half of that 400, which is 200. So when is it going to get below 1 milligram? So it looks like on the 24th day or 23 days after the person starts taking their doses, we're going to get less than 1 milligram. No matter what happens when you take a drug, you always have a small amount of it in your body. Now, another one of my favorite problems is the pool problem, which in your handout is problem number 3. So again, similar idea. We have to consider the seed number, which is the starting value. We have to consider the recursive rule. So how are we going to represent a sub n plus 1? So let me go back, exit, and exit again, and go up and delete that sequence. Now, I could do this on the home screen. But again, that's cumbersome. So let's think of what happens every day. If the sun burns off 15%, what that means is, as a decay rate of 15%, that means our decay factor is going to be 100% minus that 15% or 85%. So 85% of the chlorine remains in the pool on a day-to-day basis. And what they're doing is they're putting in the shock treatment at night after everybody leaves. So it can kill some of the algae, but during the following day, over a 24-hour period, what's going to happen is the sun's going to burn off the chlorine after it rises in the morning. And then at night, they add 45 grams. So let's enter our sequence. As we said, our seed number was going to be 450, the starting value. Our recursive rule is going to be 0.85 times a sub n plus 45. Press execute to store it. So now we got to set our table. We want to go out to, let's say, long run. Let's make this 40 days. And we want our initial value to be 450. So we got everything set in our table. I also want to take a look at the graph of this. So I'm going to pull up my second window, which, as you can see, goes from -5 to 50 and -50 to 500. I like to go a little bit below and a little bit below above the max value and the x-axis so we can see everything. So let's go to our table. And as you can see, if we scroll through our table, we're going to get the values over a period of days. So at 3 days, at 10 days, we're going to have about 329 grams of chlorine. At 3 days, about 392, but let's consider the long run value. So let's look at the plot. So we had it going out to 40 days. If we trace on this, we can get the values, and we can see that the limit is getting close to 300. So over a period of time, the threshold of chlorine, by adding 45 grams a day, is going to be 300 grams. So again, another situation when we are thinking of a threshold. Meaning if you put in too much chlorine, you can burn people. If you don't put in enough chlorine, you're not going to kill the algae. Just like with a drug situation. You have to reach a therapeutic level for certain drugs for them to be effective. Otherwise, you might have people overdosing, and if they underdose, there might be become a medical issue. So what we are talking about here is we had it. If we go back to our recursion screen, in A sub 1, we have what looks like a geometric sequence. But then we have something added to it. So this is what we call a shifted geometric sequence, where you have a common multiplier, which is your common ratio or common rate, and then the addition of a constant to that recursive rule for the geometric sequence. And the sequence will always converge if the multiplier is between -1 and +1. So notice here on this sticky that I have where the definition is located, I'm using a sub n as the current value. A sub n plus 1 is the next term. Depending upon your textbook or the terminology you want to use, you may refer to as, let's say, u sub n as the next term, and then u sub n minus 1 as the current term. It's up to you. But if you want to represent it symbolically, staying with this notation, a sub n plus 1 is always going to be equal to the ratio times a sub n plus b, or the new value is the ratio times the current value plus or minus a constant. And again, the ratio has to be between -1 and 1. Now, I know for some kids, this might be a little bit out there, but if you want to get their attention, talk about money. So here we have what I refer to as the credit card problem. And for a lot of the kids, it's an eye-opener. Because all the kids want a credit card as long as somebody else is paying the bill. So let's think of a scenario here. We've got Cece's spent $1,500 on a card 1 month. That's her balance. Then she gets laid off from her job, not going to make any more purchases, and she can only make the minimum payment. And her monthly interest rate is 1.5%. So what that means is we are going to have a growth rate of 1.5%, which has to be added on to 100%. So that tells us the growth factor is going to be 101.5% or 1.015. So again, this can be modeled on the home screen in steps. We have the interest accumulating over a monthly period, and then she makes her payment. So 1.015 times a sub n. And now she's making a $50 payment. So we got it stored. So now let's set up our table and let's go out to 50 months. And our seed number starting value was 1,500. And now I want to find out what her balance will be after 1 month and when she'll get the balance under $1,300. So we got everything set up on our table. Our equation looks good. Let's look at the table. And it looks like after 1 month, she made a $50 payment, but has only eaten into $28 or $27.50 of principal. So let's go down in our table and find out when she's going to get it under $1,300. So it's going to take 7 months. Okay. We can keep scrolling through the table. And we can see that after 2 years, she still has $712 to pay. After 3 years, she still owes $200. Hey, she's making a dent in it. Looks like she might be able to pay this off pretty soon. After 40 months, she still owes $7.63. And on the 41st month, she's paid it off. So let's think about the math of this. How much did she pay off? How much did she have to pay back that $1,500 worth of merchandise? It's going to be 40 months plus the additional $7.63. So 40 times 50 is 2,000 plus the $7.63. So a little over $2,000, $2,007.63. So this cost her $500. Let's look at the graph. Oh, I got to get my window. Excuse me. And let's go to recall 3. Execute and exit and exit and table and graph. That looks much better. Notice it's not a linear graph. And that has to do with the payments and how much money each payment, for lack of a better term, eats into the principal. The first month she only paid off $27.50 of principal. But with every successive month, she's going to pay into the principal a little bit more. And that extra amount will be a constant. You can explore that on your own. This problem has lots of good variations. So let's say she had a rich aunt or a rich uncle that was going to help her out every third month or so. You could work that in here as well. But I hope I've given you some ideas for making sequences and limits come to life, and that you can use these problems in your classes. Does anyone have any questions? If you have any questions, enter them in chat. My handout has my email address. If you have any further questions about taking this approach, please feel free to email me. But I felt it gave students a good sense for what a limit is. And it made them, when I say them, I mean limits, and the mathematics behind limits come to life, as opposed to just looking at graphs and thinking in terms of delta and epsilon and narrowing down the neighborhoods and approaching from the left and approaching from the right.
Wash your hands. Awesome. Well, thank you so much, Tom, for providing us this information tonight, and for everyone else on the call. If you would like a certificate of attendance, please feel free to reach out to Hafiz and myself. You can email us at hcon@casio.com or dshaw@casio.com, and we'd be happy to give those over to you. And also, at the end of this webinar, there will be a recording available post-event in the next couple of days. There is an additional question in the chat from Eric. Tom, it is the Casio calculator simulated that is being used on your screen?
Yes, that is the CG50. And you can model this on any of the Casio graphing calculators or almost any graphing calculator, even Desmos, as well as ClassPad. I decided to use, instead of using ClassPad, I've done this with ClassPad, but I am very, very comfortable with the CG50. So that was my tool of choice.
Excellent. Well,
I am going to see if I can share this with people, because I see in the chat there are a couple people who made requests for the paper and the link. Let me see if I can do that here. No, I really can't do that here. I think wait a second. Let me see. Let me try that again.
You might be able to press the.
I'm copying the URL, and I am going to put it into the chat. And
I just shared. I think if, can you guys confirm if everybody can see the paper that I want to just put in a chat?
And I think Bruce can see it.
Perfect.
Yep, that pulls up for me too.
So you're able to see my screens. Oh, one more thing. Let me pull this aside. Thank you again for joining. You know, as I said, real world examples of long run values and limits. You can use these problems as a hook, and something we have to keep reminding our students: don't ever give up.
Wonderful. Well, thank you so much for joining us today, and you have a wonderful night, and we'll be seeing you on the next one.
Thank you, everybody.